2. On my notes is page 2-23. Okay. Okay. Here's the problem. Specify the traction on the boundary. Right. This is the fourth boundary condition. That means the stress sigma 11 at 0t is equal to all the traction. We use the traction, okay? Traction T11 is at x0t is prescribed by a function qt. So this is a problem, okay? This is a half space problem, okay? Half space. That means this is x1 coordinate. If this is x2, x3. x2 is inside the blackboard, okay? And this is at 0, x1, 0, okay? x1, 0, right? And this is the material with the E nu as my elastic property, okay? From elasticity, we know any elastic medium can be characterized by any two material constant, either Young's modulus, Poisson ratio, or Lamé constant, shear modulus, or Young's modulus, shear modulus is equal to nu, okay? Or Bach modulus and whatever, Bach modulus and yeah. So any two, okay? You can choose and Poisson ratio probably. So you have so many kinds of elastic constants, but you can choose any two to prescribe the material property, okay? I will show later. Each one can be written. For example, lambda, if I can say, is if you can write in terms of Young's modulus and Poisson ratio. I'll show you later. And you know the shear modulus is equal to Young's modulus 2 times 1 plus nu, right? So you know this, okay? And this is equal to mu, right? So this problem is what we are going to study, right? And this is the traction is we say this in this way, right? Last time I remember is equal to qt, okay? Yeah. So before I start this problem, I want to recall your elasticity in stress-strain relation in elasticity, okay? One thing is for the strain in epsilon 11 direction is equal to what? Equal to sigma 11 over Young's modulus. And what? Poisson effect, minus or plus? Minus, right? Poisson 2,2. The strain due to 2,2 and Poisson effect will shrinkage by another direction, right? And minus the effect from sigma 3,3 over E, all right? And epsilon 2,2, the total strain in direction 2 equal to E2 sigma 2,2 over E minus nu sigma 1,1 over E minus nu sigma 3,3 over E. Is that right? And epsilon 3,3 equal to sigma 3,3, the main strain due to 3 direction, and minus the opposing effect from direction 1 and direction 2. Okay, and this can be written as what? Okay, sigma 11 over E minus nu sigma 11 over E plus sigma 22 over E plus sigma 33 over E plus nu. Right? Okay? I add 1 and I subtract 1, but I add 1 to change equal. Okay? Now I can add this together as is 1 plus nu over E sigma 11, right? Minus nu over E 11 plus 22 plus 33. Okay? Yeah. And similar for this one, can be written as 1 plus nu over E sigma 33 minus mu over E sigma 11 plus sigma 22 plus sigma 33. And this one can write 1 plus nu over E sigma 22 minus mu over E 11 plus 22 plus 33. Right? And we also can have epsilon 1, 2 equal to half gamma 1, 2. Right? This is a tensor shear strength. This is an engineer shear strength. Okay? And this will be half. And this engineer strength will be what? Sigma 1, 2 divided by G. Right? And this is equal to half. G is equal to E 2, 1 plus nu sigma 1, 2. So it's equal to 1 plus nu over E sigma 1, 2. Right? So similar, epsilon 1, 3 equal to 1 plus nu over E sigma 1, 3. Epsilon 2, 3 equal to 1 plus nu E sigma 2, 3. Okay? So, from this, I can write the general form as epsilon ij is equal to 1 plus nu over E sigma ij. And minus, right? Nu over E sigma kk delta ij. Right? So when I is equal to j, right, because it's a free tensor. If I equal to j, this equal to 1, and this will be either one terms here, right? So this is same mu over E sigma kk. So this is yeah. And for if I not equal to j, delta ij will be 0. So only this term, just for these three terms. All right. So this is a relationship. So we can have sigma ij equal to 1 plus mu over E sigma ij minus mu over E epsilon sigma kk. Delta ij. Okay? So this is what I want to show you first. Okay? So use Young's modulus as Poisson ratio to form the relationship between strength and strength of elastic material. All right? So you have to know this way, okay? To get this equation first. This equation is use stress to express strength. Now, I want to use strength to express stress. How do I do it? Okay, that's very useful. Huh? I think I have told you many times in different courses. So if I want to do this, 1 plus mu over E sigma ij will be equal to epsilon ij plus mu over E sigma kk delta ij, right? So this is I want to use strength to express stress. But here, I want to change this into strength. Okay, how do I do it? So from this equation 1, this equation 2. Okay, so from equation 2, I have a 1 plus mu over E sigma ii j sum over is equal to epsilon ii plus mu over E sigma kk delta ii j change to I. And delta ii equal to how much? 1 plus 2 plus 3 equal to 3. Alright? So I have 1 plus mu over E sigma ii equal to epsilon ii plus 3 mu over E sigma kk. Because kk is dummy, so I can change code it I. Alright? So I have sigma ii and so I have 1 minus 2 mu E sigma ii equal to epsilon ii. Okay? So I can have sigma ii equal to epsilon ii times E divided by minus 2 mu. Okay? So you call sigma ii, also you can change the name because dummy. You can call kk. kk. So this is a tensor operation. So you can change, put it back to here. So 1 plus mu over E sigma ij equal to epsilon ij plus mu over E, and the kk can be replaced by epsilon kk times E 1 minus 2 mu delta ij. So this is equal to, sorry, this is sigma kk. So I write sigma kk in terms of sigma k in terms of epsilon kk. All right? So now I get the relationship sigma ij equal to E 1 plus mu epsilon ij. Okay? And E can cancel, right? All right? And plus E 1 plus mu times mu 1 minus 2 mu epsilon kk delta ij. Okay? So I don't think you can memorize this, but I think you can derive it by yourself, as I've shown you. Okay. After you got this, you can use the technique, the trick I told you, to get the relation of this. All right. Another equation you should memorize, the Lamé constant. We have a sigma ij equal to what? Lamé constant is I will use later, I think. Let me see. Lamé constant is lambda, okay? Bark modulus delta ij plus 2 mu epsilon ij. Okay, this is another relationship you should memorize. This is a Lamé constant related to the volume strength, strong volume. Okay, yeah, I will show you later why it's. Let me see. Yeah, let me make sure first. Yeah. I forgot somewhere, maybe in the previous chapter. I say you should read by yourself. Okay. Let me see. Oh, here. Yeah. So this I want to memorize, and this mu is equal to G, the shear modulus. Okay. So compare these two equations. You can find this. This is equal to Lamé constant. Okay, and this is equal to 2 mu. So mu is equal to G as E to 1 plus mu. And the Lamé constant is equal to this one, right? E nu. 1 plus nu, 1 minus 2 nu. Okay? So this is a way to show you any elastic constant can be expressed by another two material constants. So I didn't prove the relation between mu and this, because here I directly use the as known value, but you still can show the G equal to this one. Actually, we can show from here. Okay. I can show. Once you got this equation, epsilon ij is equal to 1 plus nu over E. Sigma ij. Not good. Yeah. Let's skip this, because you should go back to check your elasticity. How to prove? Okay. G equal to E. 2 plus 1 plus nu. Okay? Okay, homework. Go home to put this. Check my notes in advanced transfer material, or you have this. I prove this. Remember? No. Okay. Go back to check. Okay? I don't want to do it. But because I use this here. When I derive this equation, I use this relationship. Yeah. Okay? You also can do the this to get a Lamé constant or Bach modules, those things. Okay? But I don't want to spend time on this. I just want to show you this is 3D elasticity. Okay? Yeah. Now, go back to the problem I have shown you. This is the x1. We have a u1. And it's a x3, u3 displacement, okay, and u2. And I have a prescribed displacement q. Remember, we have the Koch formula. T vector is n. This Koch formula. And for this boundary condition, I want to change this boundary condition in terms of stress. So stress, I have a sigma 1, 1, 1, 2, 1, 3, 1, 2, because symmetry, 2, 2, 2, 3, 1, 3, 2, 3, 3, 3. And the surface track vector n of this surface, this material, is what? The n vector. Can you tell me? Minus 1, 0, 0. And it's equal to the stress vector is what? Negative q. Is T11. And 0, 0. Right? So from here, this is T11. T11. T11 is Q. Right, Q. But in that direction. All right? So from this, I have a sigma 11 minus equal to minus Q. And minus sigma 12 equal to 0. Minus sigma 13 equal to 0. So on this boundary, the shear stress are 0. And the sigma 11 equal to Q. Q. All right? No. So if I use this relationship, so from from the sigma ij equal to lambda epsilon kk delta ij plus 2 mu epsilon